Alright, so this system of blocks is connected by a massless string. We're told that block A is 5 kilograms and block B is 2.2 kilograms. And we're told that block B falls delta S of 0.65 meters in a time of 1.5 seconds. The system is set into motion, so V0 is 0, and the amount of time that passes is 1.5 seconds. Alright, and we want to know what is the coefficient of kinetic friction between block A and the horizontal table. Alright, so I guess the first thing is to draw a free body diagram here and figure out what are the forces and the sign conventions and so on. If you haven't already done that, then you should pause the video and do that now. So let's see, for block A we've got gravity, we've got a normal force, kinetic friction, and tension. And the motion for block A is in that direction. It also moves 0.65 meters. We'll take the direction of motion to be positive for the top of the diagram here. For block B, gravity and tension. And following this sign convention around, we get that down is positive. Okay? You recognize that with a pulley you have to alter your sign convention. You have to kind of follow the pulley around. Alright, so this is motion with constant acceleration, so it can be solved either using Chapter 4 techniques or Chapter 5 techniques. So I'll start by solving it using Chapter 4 methods. You know, seeing this, I've got delta S and V0 and T. I think I can go ahead and solve for V and A. I think that's going to do me some good, so I'm going to go ahead and do that. So, alright, so if I want to solve for V, then I would use or if I want to solve for A, I'll use the equation that doesn't have V in it, and that is this equation. So this gives me an acceleration of 0.578 meters per second squared. And if I want to solve for final velocity, then I can use this equation. Which gives me a final velocity of 0.87 meters per second. I think those two quantities are going to come in handy later on. How did I know that I had to solve for that? You know, instinct. After seeing many problems in forces and motion and work and energy, whenever I'm given 3 of my 5 unknowns, I'm going to go ahead and solve for the other 2, because I'm probably going to need one of them. And as you'll see, we will need them. Alright, so using forces, let me write down the forces on mass A. So the sum of all the x forces on mass A is Ft, which is positive, points to the right. Kinetic friction, which is negative, points to the left. That's equal to MA A. We also have, I guess, the sum of all y forces is the normal force, which is positive, minus gravity, which is negative, is equal to 0. I can combine these two equations, right? If I solve for the normal force, then I can take that result and I can plug it in up here to the normal force, and I get Ft minus mu sub k mg is equal to ma. For mass B, The sum of all the y forces is gravity, which is positive because it points down, and then tension is negative because it points up. Okay. Yeah, I've got basically, okay, so I kind of got ahead of myself here. If I look at my three equations here, 1, 2, 3, I've got three unknowns. My unknowns are the tension force, and the normal force, and mu sub k, right? So in this equation, the normal force is unknown. In this equation, the tension is unknown. So I've already substituted for the tension here. I'm going to go ahead and solve this equation for tension. Tension is equal to mbg minus mba. Right, and I'm going to take that result and I'm going to plug it in up here to this first equation. So now this first equation has two substitutions in it, right? I've already substituted for Fn, now I'm going to substitute for Ft, and I'll be left with a single equation and a single unknown. So if I make that substitution, I get mbg minus mba minus mu sub k, mag, is equal to maa. Now the only unknown left in this problem is mu sub k. Right, so if I plug in everything else, I get, well, let's see. Let me isolate mu sub k, I guess. So okay, so what we've got over here on this side is 21.56 and minus, let's see, this total is 4.16, right? Because MB minus MA is, MB plus MA is 7.2, and then the acceleration is 0.578 here. So 7.2 times 0.578 is 4.16. And then on this side, I've got mu sub k times 49. So that results with mu sub k is equal to 0.36. Now, using Chapter 5 methods, I'm really going to have to scrounge for space here because I'm running out of space. We have to calculate the works done by all 6 of the forces in the problem, right? So we start with the normal force, which does no work. We have the work done by gravity on mass A, which also does no work. Both of these are perpendicular to the motion. We have the work done by kinetic friction on mass A, which is, well, let's see, mu sub k times the normal force times delta S times cosine 180. So that works out to be, right, if I make this negative 1 and I use my normal force, which mag here, that's 49. My delta S is 0.65, so that works out to be minus 31.85 times mu sub k. The work done by tension on mass A is plus Ft delta S. The work done by tension on mass B is minus Ft delta S. Right, it's Ft delta S cosine 180. And the work done by gravity on mass B is positive mg delta S, which is 14. The change in kinetic energy, delta K, is 1/2 times the total mass times the final velocity squared, minus 0, because it starts at rest. So we have the final velocity from up here, it's 0.87, so this is 2.7. That means if I add up all of the works done by all of the forces, I get minus 31.85 mu sub k plus 14 is equal to 2.7. So if I solve that for mu sub k, I get 0.36.